Okay, I'll start over from this slide since we're now recording. Why partition communication? Why is the status quo not working or not going to work in the future? MPI use cases continue to evolve. What we mean by this is that we have more cores and hardware threads and this MPI plus X infrastructure where we may not want to filter down to a single thread to do communication. And this gets even worse when you start looking at doing communication from accelerators, right? All of a sudden you have a bunch of threads that don't like to diverge within a warp. And so it makes a lot more sense to have communication be controlled by individual threads. But this has been, one of the options here is to historically been to use different MPI processes on a single node without threading. But that, as we'll see in a minute, tends to lead to an explosion of matching and rank space. And there are some other solutions to this, but what we really want to see is, if there's a MPI or a way to use MPI, or we want to build a way to use MPI for concurrent communication. So it's off to the side. The coming thread storm. What we did here was an evaluation of MPI matching, right? So if you did this with just send receive and made fine-grained communication, how bad would things get? We looked at a 7-point and a 27-point stencil for Halo codes, which are both pretty typical of what you would see. And talking to the to some of our local applications developers, they aim to have an iteration time underneath this gray bar. So by the time that the bars here reach this gray area, we're already spending more or as much or all of our iteration time, all of our target iteration time for these codes in matching. And you can see as we get more and more threads and do different thread decompositions, and so we have more threads on the surface space to communicate, this gets worse and worse and worse. And gets to an unacceptable level by the time we hit 56 threads, which is doable in today's systems. So what is partition communication? Well, the idea here was to take a lot of the, to make a two-sided communication interface, much like what you've seen before, but to split that up among threads. So what I mean here is that there's the same number of messages as we sent before. We're not adding ranks or sub-ranks to this to differentiate, but we are having multiple threads working together to assemble a message, right? So MPI only manages completion notification, and you have, to manage that, you need simply actor and action counts, not collectives of any kind. So it's very lightweight. We have persistent style communication. So what this means is that instead of doing your turning your I send and your I receive, or your send and receive into a partition call, you will need to look at persistent communication where you init a request, start it, and then the usual test wait that you'd have on an I send, I receive pair, and then freeing it afterwards. But what this allows you to do is restart communication calls and essentially reuse these requests. This is important for partition communication because there's a bit more overhead in setting up the networked request for fine-grained a fine-grained interface. And to do fine-grained communication, if we want to send pieces of the message as they become ready, we can do this without doing any major thread concurrency or thread handling. We can leave placement to the user, and a lot of the stuff that we're doing behind the scenes simply needs a count of number of workers and the number of workers that have currently called ready on their data, which can be done with a single atomic. And we don't need to have separate data patching and separate send structures, which can complicate user code. And we can send the data as it becomes available. So really what we're trying to get here is what we call early bird communication, which is a new kind of overlap where early threads can start moving data right away, or MPI can start moving data right away as data is marked ready. So the bottom graph here, or the bottom figure here, is what we do today, which is we wait for all the threads to arrive at the communication point, and then we have a single thread send all of the data after that. And what we're trying to do is get to the top figure where as thread 1 arrives, it can start its data transfer. Thread 2 may have to wait for thread 1 to complete depending upon network availability, but it can queue that up to be sent. And this way we only have to wait, or we don't only have to wait in this particular case for thread 4's data to transfer after it has arrived, or after the thread 4 has marked its data ready to start the next iteration. And we can, we've implemented this in the past over RDMA to avoid message matching, which gets rid of and a lot of the other MPI overhead. So persistent partition buffers. As with any communication, we have to have an input buffer and an output buffer, where your data originates from, as far as MPI is concerned, and where your data is going to be placed. We, in this model, share ownership of these buffers because we're doing persistent communication, so that MPI can do its communication while computation is going on and the other parts of that buffer are modified. the MPI, or we need to describe the operation before contributing segments in this method, which means we need to know if we're sending or receiving data, and it needs to be set up before the data starts getting marked ready, so that we can set up the communication structure well beforehand. And again, it helps to reuse this to get rid of, or to amortize most of the overhead. MPI implementations don't have to care about sharing. It really only, as we said, it only needs understand how many times it will be called and how many times it's currently been called. And this can be managed with atomics. Threads are required to manage their own buffer ownership, which essentially means the user has a little bit more on them to make sure that once a ready call is called on a particular partition, they cannot change that until they know that the communication is complete. Otherwise, there's undefined behavior. So P-ready or MPI P-ready should only be called on or partitions of the buffer that are complete. Threads are required to manage, and again, this can be handled with atomics from the MPI side. So a quick example of persistence. If you haven't seen this before, you need to initialize the setup. This is the header for the function called for an MPI partitioned send init. The request needs to be started after that. So it's not, you can or initialize a buff or a request that gives you the request handle, tells MPI that everything's going to get, that this exists. Start moves it into the active category. Now we need to add items to this buffer. I've mentioned MPI P-ready before. This is the actual call that you can, or that you would need to make. I think this has changed since I forgot to update the slide. At the moment, it doesn't take in a buff. It doesn't take, or it just takes in a partition number and the request. Apologies for the dated call. And then you need to wait on completion. There's also an MPI P arrived call that mimics P ready on the receiver side. So I can ask if an individual receive side partition is ready. And this start P ready wait loop can be executed or can be reused as many times as long as the partition send is the same. So using partcom in an MPI program, the things to keep in mind here is that you're going to need parallelism in your data structures. A lot of what Pepper's going to talk about is going to be doing this for proxy app mini-FE, and not what you have to do in terms of a basic conversion, a first order conversion, without changing the data structures underneath to be inherently more parallel. But you also need to balance communication granularity with overlap. It doesn't make sense to cut things down into single bytes. or even, 100 bytes or anything like that. What we found is that if we have messages on the order of 64 bytes to 1 MB, we see good performance with 32 to 64 partitions with micro benchmarks. That leads to partition sizes of about 1 GB to 64 GB. This gets us into the range where we're bandwidth limited rather than latency limited, so that we're not adding a lot of overhead as we add more partitions or subdivide into more partitions. And there's a need to have a high quality partition communication implementation for benefit to be seen out of this. If you're using something like a interface that reduces down to send receive, you're still going to incur those send receive costs. So what is MPI doing to help? When designing your application, keep in mind what they're doing, the implementation that you're using is doing. Think about overlap as early as you can call preready and know that you're not going to edit that partition of data. You need to send it. All systems have noise, whether it's from hardware variability between different different CPUs on the multi-CPU board, or noise from the operating system. And this can lead to a potential source of overlap as well for communication. Because we can't control these, we might as well use them to get more network performance. And then again, consider overheads. Don't send very small partitions back to back, because there's overhead with function calls, and while we can do aggregation on the MPI side, there's still overheads there. So opportunities for optimization. MPI implementations can optimize data transfer under the covers. We can, there's opportunities for aggregation. So we could, if you specify or over specify or have more partitions than the network can handle, or not the network can handle, the network can use performantly. MPI could theoretically aggregate these underneath the hood. It could be optimized to specific networks, including looking at their MTU size, and the overall number of transfers, if you're mapping your partitions to threads and tasks, would be between 1 and the number of threads, or the number of ready calls that you, or the number of partitions you told MPI that you have. This reduces the total number of messages sent, decreasing the overheads for matching. So we looked at this from the perspective of so we built a micro benchmark that essentially looks at partition communication and tries to emulate noise in the application. We have 3 graphs here. They're all bandwidth curves, and it's important to note that the y-axis here is perceived bandwidth, as defined earlier, which is how much time or how much bandwidth does it look like if I were to synchronize after all the threads are finished with computation to the point at which communication is done, right? So we can, by that logic, have bandwidths here that are higher than the actual network bandwidth because we're not factoring in overlap. And so this is how we're measuring the effectiveness of overlap. You'll also notice that we ran these on the Knight's Landing architecture using different compute sizes and different noise sizes. So if you look at the middle figure here, we ran this with a 100 millisecond compute that was perturbed by 1% noise on a single thread. And so as you see here, you know, that below about 1 megabyte, especially in the what's that, the oh, I should also go into, so the green lines are fine points or partition communication, as it's called now. The blue lines are multi-send, which means that we're doing I-sends, but we're doing them in a fine-grained manner. And the red line is our baseline, where we wait for all the threads to finish, and then we send a single monolithic send. As you can see, after about 1 megabyte, fine points or partition communication starts doing better than multi-send, because it gets rid of the overhead, and it does better than waiting for a all the threads to finish and do a single send. So below about that size of message, you may want to look at doing a single send. So this is an example program. This is just the benchmark. As you can see, we have 2 ranks, a configurable amount of noise, a configurable or compute time. We have the rank 0 is initializing a partition send, while rank 1 is initializing a partition receive. And we're setting up some sleep times here. We have a parallel loop where each thread, one thread's getting perturbed so that its sleep time is longer by using the compute time plus the compute time times the noise. And then we start our iterations where we start the request only on the master thread. We then hit a MPI barrier to make sure that everything started, which isn't necessary for that, but can be good practice. And then a pragma OMP barrier, which is important because we can't call p-ready until or the request is started, which means that we need that or master thread to complete the start call before we can continue on. We start a timer. We end the timer there. Wait, am I missing a slide? I appear to be missing a slide. So after this, what we would do is have a P-ready call after this barrier on each of the threads using the thread ID as the index into their into the partitioned as the partition number for P-ready. From there, we get the duration, subtract out the compute time, and print the statistics. And after reusing this multiple times for the request multiple times for the for each iteration, we then call free on the request. So takeaways, partition communication is useful for concurrent programming models. It allows us to send data close to computation. It's not a bulk synchronous model. And we're actively looking into how to get this on accelerators and GPUs so that this can get rid of a lot of the MPI overhead in future MPIs. If we want to look a little bit more at GPU communication, what's currently being talked about is adding in another call within MPI, and such as a pbuff repair, because one of the challenges here is that on the receiver side, you don't MPI start has to be non-blocking, which means that a return of MPI start on the sender side doesn't mean that the receiver side is ready to receive data. And so there's a little bit of overhead still there. One way that we can get around this is by having a separate call, in this case, MPI pbuff repair, that is a blocking call on the sender side and a non-blocking call on the receiver, where the receiver essentially gives a ready to receive flag to the sender. At that point, we can do, the idea would be that we could do MPI P-readies, potentially a device-specific MPI P-ready call to differentiate it from the GPU kernel. These are what we'd expect the call structures to look like for pbuff repair. It looks very similar. Another name that has been considered for it was MPI psync. That's a little bit dated at this point, but it's still in active development at the MPI forum. And with that, I will take questions and then hand it over to Pepper. So the initial part of, to answer Brian's question, the initial part of partition communication is in the 4.0 MPI standard that was released, I believe, last year or the year before. I'm trying to remember dates at this point. It's not, so any MPI that fully supports MPI 4.0 should have it. I don't think, or like we're looking at initial releases for Open MPI with some initial MPI 4 support, but not the full thing. I think Howard can probably go into more of that than I can. But if you have any questions, raise your hand. And I don't think there were any questions on. Okay, with that, I will hand it over to Pepper to talk about his experience in converting MiniFE to partitioned communication.
Awesome. Thanks, Matt. So as Matt said, my name is Pepper Marks. I work at Sandia National Labs as an intern, as well as at UNM as a PhD student under Patrick Bridges. And I'm going to talk to you today about my experience, actually implementing fine-grained communication. The majority of this talk is going to be about partition communication, but some of the concepts apply a little broader. Next slide, please. I already went over this. So next slide. Cool. So for the most part, there are three major tasks you need to complete to take an existing application and modify it to use fine-grained communication. And those fall into mapping data elements to communicated partitions, packing and marking ready from a threaded context, and tuning the partitioning for the best performance. All of these were mentioned in brief by Matt, but we're going to go over it sort of in a more start to finish way here in this talk. Next slide. So starting with the first one, this is a quite variable process depending on the application you're modifying. In particular, it modifies greatly depending on the possibility of coupling between thread and partition. So if you have something where basically there is a single communicated partition per thread and you just call ready at join, this can be an incredibly straightforward process. The only issue is that doesn't actually map very well to existing Halo communication. In particular, with my experiences with MiniFE. In our experience, what we ended up doing in our Halo codes is separating our send buffers into partitioning and managing an application side map from computed element into individual partitions to mark ready on. Next slide, please. So, for example, it would look something like this. We would have to have data structures to manage a variety of communication questions. Obvious ones are, because we're doing this in a threaded context, we need to be calling it we need to be interacting with this on a data element by data element level, as opposed to at a thread by thread level. So for each element, we have to say, is this element sent? To whom is it sent? Because it could be sent to multiple recipients. Where is it packed? I.e., what buffer, if any, it has to be packed into, and what partition does that place in that buffer correspond to? Simultaneously, only once it's filled do we necessarily want to call ready on it. And so we end up with this large mass of data structures just to handle the complexities of marking P ready. Here's some example code going over the general concept. And at the end of the day, what was, just your tight loop has, bloated a fair amount in pursuit of this. Next slide. However, that's just considering the data structures. What is actually necessary information? Obviously, the nature of this beast is that this is largely designed to handle hardware threading. And we need to make sure that the thread safety of these concurrent counters and data structures is sufficient and performant. And there's a real impact there and a lot of thought process that has to go into actually managing that. Next slide. So a big part of this is really being careful about packing and readying. In order to actually get the benefits of partition communication, you have to pack at completion, potentially element by element. Yes, conceivably, you can do this later, like at a thread join, handle everything that is handled by that thread. But in order to actually maximize the potential benefit, you need to be doing this effectively in your compute loop. And that is a serious ask. This requires the use of thread safe structures from this threaded context. And that means that they have to have, low atomic counts ideally, and low cache impact in order to make this in order to make the overhead of handling these sort of complexities smaller than the performance gain from better utilization of network resources. Next slide. So here's an example of an existing MiniFE Waxby function. This is just taking two vectors, multiplying each one by a different scalar, adding them together. A very straightforward core compute loop in MiniFE. For example, any communicated element, this is the last thing that touches them before they're sent over the wire. If we look instead and see what it looks like in my work in MiniFE, which is a fine-grained communication code framework that I am using and for my own research, we see that it bloats fairly dramatically. It has a lot of similar structures to what I described in the example code. We see that what once was simply one line of computation now has the potential of being much more. The main thing to remember here is that if possible shortcut. Ideally, in our tight loop, we go from most of the iterations through, or all of the iterations through, just being those two multiplies, one addition, a lookup, and a set, to being those same numerical operations and one comparator. That's not a dramatic impact for the majority of times through the loop. However, when we do actually find a sent partition, we want to be very careful. So a really key thing is making sure you use quick data structures. For example, if your code base is small enough, having direct lookup through arrays. If you have larger counts, if these data structures have to be larger to handle larger global IT spaces, having fast access maps, hash maps, these are very important considerations. If we go through this code in particular, you'll notice that besides the lookups, we're doing a pack in here. And we're doing two atomic operations. So this is very important to minimize. If you want to keep your work performant, it's shortcutting and really, if at all possible, minimizing the amount of atomic operations you have, which means, if possible, simplifying your data structures for your maps between partitions and elements. Next slide. The third part of this talk is about the granularity of sends. And really, at the end of the day, when you're talking about actually leveraging the potential for early bird communication and reduction in iteration times due to reduction in computation times, we find that actually leveraging that performance benefit really, really depends, like Matthew said, on the aggregation, on the actual size of the partitionings and how we're splitting up existing structures to be sent over the network into partitions to send over the network. Next slide. In general, there are two major takeaways, and that is, at the end of the day, you need to have a partition count large enough that you're likely to have individual members calling ready well in advance of the last thread to mark their partition. That's the actual time frame between basically the first mark ready and the last mark ready that we have to leverage early bird communication and reduce ultimate communication times. So if your messages are too big, what you end up doing is actually reducing the time between the first thread to mark partition ready and the last thread to mark partition ready. So we want to maximize the potential for early bird communication. Simultaneously, if your messages are too small, you end up not saturating the network and having the overhead of many more calls into MPI or your library of choice. So in general, you want to ideally be sending something on the order of your MTU. You want to be actually sending, messages of size necessary to actually saturate the network without, but still having them be small enough to actually reach these thresholds. There are lots of other potential interesting areas in this space, depending on methodology of choosing these partitions. What I've described here is basically a linear division of your communicated volume into partitions. That is not a necessary thing, but there's a lot of interesting space here for optimizing this both to your machine in particular and the nature of your threading in your application. Next slide. Or, yeah. Are there any questions on what I went over?
There's one question in the chat, and Brian, if you want to ask it yourself, that you can unmute now, or I can ask it.
Yeah.
I can ask it. It's in MiniFE is, it looks like you're using, it's hidden behind abstraction, but you're using
exactly.
thread, atomic.
Yeah, so what
okay.
I can answer this. So we are using std atomic in the version of MiniFE I wrote for a point of clarification up front. Most of my work in fine-grained communication has not been directly using partition communication. It's been using a framework that I published called Minimod, which is basically a configuration layer that allows you to design fine-grained applications and then vary at runtime the actual implementation of threading and communication under the hood. But in my experience, what we've mostly done is we've used OpenMP to handle threads. So we're not necessarily using the we're not using the C++ standard threads library, but we are using std atomics as our choice of atomicity.
That's pretty typical, I notice.
Mm-hmm.
So far, it always interoperates and it never breaks, so I'm pretty happy.
There have been, so I have to be careful of my phrasing on this, but one of the things about working at Sandia is we have great access to ARM machines, and it does seem that there might be some differences in the atomicity guarantees on ARM implementations. In particular, I think the issues I had run into had to do with pointer dereferencing, but absolutely, for the most part, you can trust your std atomics and to play nicely with OpenMP.
Yeah, I won't belabor it. This is a kind of a side point, but once you start talking fine-grained communication, this is the next thing you hit.
Absolutely.
Right? All right, thanks.
Cool. Any other questions? Thank you, everyone. Oh, wait 1 second. I see. Yeah. Thank you, Matthew. If anyone has any other questions, I'll be in the chat. I'll be able to answer them, as they come in.
With that, we're going to turn it over to Jan, who is another Sandian, who will be talking about user-level threaded support in OpenMPI.
Very good. Thank you, Matthew. Thank you for the introduction. Hello, everybody, and welcome to this topic. So the motivation behind this topic is that we typically know what MPI plus X is, and we also know that MPI plus X or hybrid execution scenarios with MPI plus some other host node or node local programming model is at least a controversial topic because of performance considerations, programmability, interoperability. And especially to have a tie-in to partition communication with the advent of this API that Matthew described, MPI is looking really good in supporting hybrid execution models where we call into MPI from a massive number of threads. Now we know on GPU devices where the threads are coming from and how the architecture looks like. And on the host side as well, we have programming models that favor massive degrees of concurrency extraordinarily well, and they are often referred to as user-level threads. So in this talk, I would like to show you how user-level threading is supported in MPI, and give also motivation that with partitioned communication, for example, MPI plus X or hybrid executions will or are becoming very interesting. A quick definition of what a user-level threading library is. Basically, it's a parallel programming model that has one property in common, and that property is that the execution abstraction, may it be a task or a stream or a thread, are not visible to the operating system. Now, this has advantages and also a disadvantage. The advantage is that the creation and disposal of a task is extraordinarily quick and cheap, as well as scheduling operations are cheap because it's basically an operation into a thread local storage and a lookup in a hash table. There is no kernel call involved. Now the problem with this is the nature of being of requiring a cooperative multi-threading. This is another important property where tasks need to cooperate in order to guarantee progress. A user level threading library doesn't guarantee progress based on a thread scheduling by the operating system. This is the big difference to, for example, pthreads. Now, in order to guarantee progress, we had to come up with something, and we came up with support of user level threading libraries in OpenMPI. And this brings me to this first slide, where I'm listing here that user level threading libraries, in particular 2 of them, are supported in OpenMPI 4.x and MPICH 3.4.x. In particular, the support that we added, and that you can use as of today, is the support for 2 user level threading libraries, namely Argobots and Qthreads. We have more libraries, support for more libraries coming in. For example, we are collaborating on the integration of HPX. How can you configure MPI to support your user level threading library? Well, you can specify a configure option, and I'm listing the configure options here for both common implementations. If you are an MPI user and you would like to see, okay, does my MPI installation support one or the other user level threading library, you can type in OMPI_info and see with what configure flags or options your MPI installation has been made. So to summarize, user level threading support requires progress guarantees, and the new feature here is that we are guaranteeing in OpenMPI, in both MPICH and OpenMPI, that we periodically call into the user level threading scheduler in order to give the scheduler the opportunity to switch tasks and schedule another task in, so you would avoid potential deadlock situations. Now, we wanted to also experiment with user level threading and also in the context of partition communication. So we came up with a benchmarking suite that is called MPI Partix. Thank you for the slide switch. So we developed an application that is called, or a suite that is called MPI Partix that has 2 interesting things to it. First, it abstracts from user level threading libraries. Thus, we include a set of APIs that allow you to create a task, wait on a task, initialize, and then also to synchronize, or basically have an atomic access, or in other words, a mutex. So currently we support mutexes, since that's the potentially less performant but more universal API. Now, an application might look like shown here in the example code. So you can initialize with Partix in it. Then you can have a loop over any number of tasks. You create Partix tasks. You pass it a function pointer and a context, and then you wait on that context, and you finalize the library. With that context, this is an implementation that doesn't depend on a compiler. So we simply create a context in the given lexical scope, which is here in the main method. And in this way, we associate tasks so we can implement a Partix task wait. Next slide, please. Okay, now, as I mentioned, correctness, or in other words, progress guarantees are important. And MPI Partix includes 2 types of examples or applications. One group that tests correctness and the other one that tests performance. Here, I'm showing an example that exercises all those requirements required from an MPI implementation in order to guarantee progress. So in this example, we create a parallel region, if we use the OpenMP backend, and we create a whole bunch of tasks. And then on the right-hand side of the slide, you see the sources behind those tasks, or basically the bodies, the task body of these slides, of these tasks. And you will see quickly that in line 8 and in line 8 of both of these tasks, we have an MPI wait. It's a blocking operation. Now, without the support of user-level threading in MPI, you would potentially, you would always deadlock in situations where the number of tasks is superior to the number of physical threads. Why? Because if the instantiation order in this case is such that we schedule the receiver task first, the receiver task will always wait and occupy a running thread. Thus, the scheduler will never interrupt the execution, will not relinquish the use of a CPU, and will not be able to schedule a task send, for example, the sender task on that thread in order to progress the computation. So with user-level threading support in MPI and MPH, we support argobots and queue threads that this always executes. However, to support OpenMP tasks, we require another concept which we are working on, which is MPI continuations. MPI continuations basically offload or basically implement a callback-based mechanism to implement progress guarantees versus a polling-based approach that we have implemented already. Both are running parallel, so they are complementary, and we are currently looking into comparison of polling-based and callback-based support of user-level threading library. That's one of our R&D directions. Next slide, please. Okay, and also we looked briefly at performance with partitioned communication. So MPI Partix includes 6 benchmarks. This is bench 1 that basically shows that things are working, we progress, even if we have an MPI wait on a partitioned communication request, that we progress. And here what we would expect is the same performance for our 3 backend implementation that I'm showing here, where we run a benchmark configured with the pthreads backend, with the qthreads backend, and with the OpenMP task backend. And in each of these graphs, we have an x-axis and a y-axis. On the x-axis, we have a certain buffer size ranging for a very small buffer to a buffer of 2 gigabytes. And then on the y-axis, we show the bandwidth in megabytes that we achieved on an x86 node with Intel's OmniPath running these 3 different backends. And we see that, of course, the maximal bandwidth that we achieved is comparable because that's the hardware limitation there. But we also see that the user-level threading implementations, such as qthreads and OpenMP tasks, achieve higher bandwidth for smaller message sizes, which translates to smaller startup time or cheaper startup time for the tasks in qthreads and OpenMP. And currently, we are taking a closer look why the performance drops for executions with many tasks, for example, for an oversubscribed system where we see that pthread scales for 1 to 8 pthreads relatively nicely. So these execution runs with different number of threads correspond to the lines that we see. However, qthreads and OpenMP tasks degrade in performance with an increasing number of threads. So we are currently investigating if scheduling decisions or the calling into the polling of the threading scheduler has an effect, and to which extent it has the effect. We have different examples and benchmarks in that suite if you would like to consider experimenting also with partition communication per se, as well as the user-level threading integration, where we simulate an overlap of computation and communication. And of course, when we measure the the bandwidth achieved with a potential overlap and measure the perceived bandwidth of that benchmark, we see a significantly better bandwidth result. Feel free to reach out to me regarding user-level threading and the hybrid MPI execution scenarios. We are looking into MPI continuations, refining this, adding also more user-level threading libraries to this. And I'd be happy to discuss MPI plus X and success stories or use cases going forward. Thank you.
Thank you, Jan. Before we move on, if anyone has a question, feel free to unmute and ask. Okay, with that, we'll move over to Howard Pritchard, who will be talking about MPI Sessions.
Oh, okay. Thanks. So this is going to be kind of brief. It's more just a, if you haven't been keeping up with what we've added to the MPI 4 standard, which came out last summer. This is more of just an overview of a new feature, not so much a detailed tutorial. It's an overview. And like earlier when Matt was introducing to all, Howard Pritchard from Los Alamos National Lab. Let's go to the next slide. Why is my thing not working? It should be working. Anyway, so Sessions represents a new way to initialize and finalize MPI resources. That's sort of an overloaded term a little bit here, but didn't include a motivation because I guess we've been working on this so long, we kind of a little bit lost sight of what it was. But one of the things actually that started down this whole path of there's got to be a different way to allocate resources from an MPI implementation in running processes was the fact that actually there's no way to initialize MPI in a thread safe manner, really. Spent a long time discussing this, but especially in an application that has multiple components. And then that led from one thing to the other. And then we, a lot of it driven by Jeff Squires from Cisco, was maybe we should really rethink this whole idea of how you initialize MPI, because if you worked with other communication packages outside of the HPC world, there usually isn't this concept that there's one kind of on and off button. And so Sessions is a way to make it less of an on and off button. An application, unlike with init and finalize, which in the I'll mention it here too. In the MPI 4 standard, we talk about a world process model or world model and a sessions model, and that terminology is used extensively through the standard, where there are relevant sections that need to be updated. But an application, for instance, with multiple components, libraries, each library in theory could use its own session to allocate the MPI resources it needs to finalize them when it's, for instance, DL closed. Also, unlike in the world model, you can, for instance, create a whole bunch of sessions and finalize all those sessions and run along without any MPI at all, and then start again with a new session, and so on and so forth. It is compatible with the using MPI init and finalize. So if you every application, I guess, out there that uses it right now, it's using init and finalize or init threading. You could take, for instance, your HDF5 library, let's say, and use sessions and create your own communicators and not really have to worry too much about the applications doing unless it's supplying you its own communicator. However, it's important to note that MPI-COM world and MPI-COM self are not available unless you use the world process model. And on the right side, I kind of have a little diagram, which is pretty close to what's actually in the MPI 4 standard of the high-level view of the flow, series of calls to use sessions. There's a call to an MPI session init, and then there are various ways once you you are returned a session handle from session init, and this can be used as an argument to additional new functions in MPI to query about what we call process sets, which I will talk a little bit about in the next slide. And then once you're ready to create a group, you can create a group from the session P set, and then you can use group manipulation functions to do what you'd like to with that group within each processing that initializes the session, and is using that process set. And then you can create a communicator using this MPI com create from group method. But there's also a similar one for intercom create from group. Then you could do, once you get a communicator, it's pretty much anything else you want to do. You could use communication, you could do one-sided or whatever, because the changes done to support sessions actually in both implementations don't really have too much to do with all the data transfer and file operations and window operations that go on inside MPI. Then finally, when your component that initializes session is ready to be done with using MPI, there's an MPI session finalize. Somewhat like, however, with MPI finalize, you want to make sure that all of the receives to match outstanding sends have been posted on the communicators you derived from this session. Otherwise, you'll end up in the same kind of situation you would with MPI finalize if someone was trying to send and no one posted. Let's go to the next slide. Okay, process sets. If we have time, I think yes, okay. So the process sets are basically the mechanism that allows the runtime to provide, give the application an idea of what resources are available to the MPI processes that were launched. Each process set has the notion of a name, and 2 process sets are currently mandated by the MPI 4 standard. That's an MPI world, which you can kind of imagine is somewhat equivalent to the set of processes that constitute MPI com world and world process model, and then self. Additional processes may be defined by the runtime. However, unless they are, the names of these process sets decided to put into the standard, they have a URI format, and the MPI colon is claimed by the MPI forum and for in process sets going forward that are part of the standard. There can be others that are prefixed with something additional. Finally, the last bullet there on the left, I included this because this came up with a bit of discussion in terms of getting this sessions added to the MPI 4 standard. So either, I'll just read it. If 2 MPI processes get the same process set name, then the intersection of the 2 process sets shall be either the empty set or identical to the union of the 2 process sets. And illustrating on the right, and there's a similar figure in the standard, MPI world is an example of the union of the 2 process sets case, where each of the little circles at the bottom, which represent MPI processes, all see MPI world when they get the list of process set names from that MPI, those query functions I mentioned in the previous slide, and they're all in it. However, each one also gets a self process set, but that self only contains that process, so there's no overlap between the self process set across the set of processes in the job. There can be application specified process set names, like here we have ocean and atmosphere, and those can be set, and the implementations are available as part of the MPI exec launch command line. Okay, let's go to the next slide. Something that we also had to change as part of this sessions proposal was there are more functions that can be called before MPI init or session init and after MPI finalize or session finalize. And this is partly because the session init has info and error handler arguments. And so basically all of the MPI info methods now can be invoked or allowed to. A implementation is supporting the MPI 4 compliant has to support invocations and MPI info related functions before MPI is initialized. Some of the others have been there for a while, like MPI initialize and MPI finalize, and get version and get library version. The session create error handler functions are also have to be invocable before MPI net or MPI final or MPI session net. And then there are a few others like the info FTC and CF and error handler FTC. Let's go to the next slide. And I think we're almost an important thing. So this is available, the sessions interface in MPICH 4. As far as I can tell, it is. And then in Open MPI, we will be supporting it in the upcoming 5.0 release. And I'm not able to give a date for that, although it's hopefully going to be before the end of the year. Let's go to the next slide. And I left this in here just for, we'll have a BOF next week for MPI in general. And we're going to present this again, but for people who don't plan to attend, this is more like what we're doing going forward. On the right-hand side, if you can see it, we have, I'm illustrating the triad that we talk about in terms of our working group for futures for sessions, where there's the application space, there's the resource manager space, and a circle on the lower left, and then the system faults and failure, where faults and failures are supposed to be reported if they could to us. And what we're looking at is actually one of the longer term goals with sessions was to be able to support workflows that don't typically match so well to the classical HPC applications. If you work with AI, PyTorch or one of these task parallel type of frameworks like the Dask framework, we want to be able to support, and I'm just not going to go through the bullets, I'll just say in general, models where processes can be started and stopped, and like under the hood of a runtime, subset of the task can use MPI, where, for instance, for a intensive part of a task DAG, but not all of the tasks have to use MPI. Those are one of the main features we're looking at. It's proving to be quite interesting to try and figure out how to do this in some way. And the other thing, as far as working group activities, we're working closely with the FT fault tolerant group because there's some overlap, particularly for process failure and restart, where we will want to make sure we're adding these kinds of features in a well thought out and consistent manner to an MPI 5. I think that is it. Any questions? I'll turn it back to you. Are you the one who's driving, Jan?
No, it's me, Matthew.
Okay. Thank you.
All right. Well, thanks everyone. I will stop sharing my screen at this point. We have a good 17 minutes before the end of the tutorial. If anyone has questions, feel free to unmute and ask anyone of us.
Hello?
Hello?
Oh, okay. So you hear me well. So my name is Ernesto Prudencio. I work at Schlumberger. So this question might be completely off the topic here. It's just so I have been using MPI for many years, and I used a lot about 10 years ago. Then I returned to use about 1 year ago. But about 10 years ago, I was working on Markov chain Monte Carlo algorithms. And in that context, for example, we had to run many so we would run many small chains in parallel. And so each of these chains would be completely independent of the other. And then at some point, the knowledge gained by all these chains should be collected and analyzed and blah, blah, and then go to the next phase. Bottom line is, so each chain would require, let's say, 1 node or 4 nodes to run a specific physical code. So we would explore the physical behavior of a code with different parameters, right, given by the Markov chain, etc. So at the time, for example, if one of the chains, if one of the nodes, so let's say we are using 1,000 nodes in chunks of 4, each 4 nodes dedicated to a specific small chain. So if one node fails, we don't need to stop all the other 249 explorations going on 4 nodes each. I remember at that time there was no fault tolerance available in MPI that we could maintain the MPI con world, let's say. So MPI underneath would say, oh, okay, this node went away. We can continue the other guys. So that's why I maybe, sorry if the question is completely out of the scope here. I'm just curious to know, was there any progress? I'm talking about this about 8 or 10 years ago. And I remember I brought up this, at the time I used to work at UT Austin, and I brought this to, I think it was some DOE meeting, I don't remember where, but, and it was a novelty. Say, oh, this is the first time we hear specifically for an application that really doesn't matter if one node goes away, etc. So anything that people could update me on that, please?
So as far as I know, there hasn't been any changes to availability for actual calls that will allow you to do that. It's been a really large topic of conversation in the standardizations body, and it's a problem that we're looking at. There was the ULFM proposal for a while that hasn't gotten standardized, but
okay.
There's a lot of work in that vein. I don't know if we have anyone who's
so just to complete my question, I remember at the time, I don't remember who talked, I think it was someone related to Open MPI, but I'm not sure. I think one idea that was floating around before even I talked about that was, oh, okay, for example, you can allocate 1,002 nodes just in case one fails, you have another one that MPI management right code would be aware there are 2 extra nodes. So in case one fails, you could just, or let's say in this case that I gave an example, I'm using four nodes for each exploration of a chain. So I just allocate 4 more nodes, for example, just in case I want to have 1 extra chain, just to be ready to be, because of course we are going to delay the other 249 because, but anyway, so I don't know if that idea continues as well, that one node that is extra could replace one node that goes down. So.
Yeah, no, that's the idea. But behind a lot of the current proposals that are being developed for fault tolerance is making it so that MPI errors aren't fatal to the entire job, and if a node goes down, you can theoretically resize the MPI COM world. As far as I know, none of those have been included in the standard to this point. I think there's been some demo implementations of them, but it's still an active topic of conversation.
And would you say that there's no big demand for that? Because there are some kind of applications, for example, we are solving a PDE. If one subdomain goes down, I mean, yeah, you're solving a linear system or a nonlinear system. Yeah, it's difficult to, there's no way. But in case where it's kind of these little pieces embarrassed in parallel. Yeah, but it seems there's no big demand for that, because if there was a big demand, these would be in production already, I suppose. I mean, I hear him brainstorm. I'm not criticizing or anything, just trying to.
So yes, wait, Matt, let me jump in here because kind of is my role as a release manager for Open MPI. So I cannot answer, I can answer from that. In the not yet released 5.0 series of Open MPI, we do support all of the ULFM functionality that's in the current ULFM proposal. And I don't remember, I assume if we're behaving ourselves, we call them with MPI X. But in addition to that, as part of that ULFM support, with Open MPI 5 and Master by default, actually, unless you're using a I have to qualify this. The model there is more like if a node goes down, but you don't have don't have an outstanding send to that to a process on that was on that node, then if we coded right and you are not using, for instance, the PIMX built with Slurm and using srun in case of Slurm, and I don't know if JSRun can support this. But if you're using our MPI run launcher, then you may have to set like an option on the launch line. Then it will just let you keep on going. If you need to do collectives, then you need to go read the ULFM proposal and find out how to repair your communicator. But at least in the Open MPI master, and no, we're main now, our main branch and what will be 5. We do nominally support the ULFM functionality and the fault tolerance model that goes with that.
Okay, that's great. Yeah, so if I remember correctly,
try it out.
Okay. Yeah, if I remember correctly from the time I was working on this, for example, if me as the application or the chain manager, right, the one that's managing all these little chains and blah, blah, blah. If I'm notified by MPIA, node 901 failed. Okay, what was the chain being handled by that? Oh, chain number, right, 700 is done. Okay, I can live with the other 249 chains and continue. That's okay. So I don't even need to, right? And I remember, for example, the head node of each of these small chains, they would communicate among themselves. So all I need to do, I remember, would be just to form a new communicator that has one less participant, and that's fine. As long as MPI can live with the fact that, okay, because I remember rarely in the code we were using MPI conworld, because as soon as the code started, we would create these smaller communicators and the head of each communicator would communicate among themselves, blah, blah, blah. So, okay, sounds good. I think it's interesting. Thank you for the update.
We still have a little bit of time left if anyone else has a question. All right, I guess with that, we will call this tutorial to a close. Thanks again to all the speakers, and yeah, have a wonderful rest of your day.
Thank you.
Thank you very much.
Thank you, everybody. Bye.